Hi everyone, welcome to my presentation. I'm Mengxuan Zhang, and my topic today is an experimental evaluation and guideline for pathfinding in weighted dynamic network. I finished this work in collaboration with Professor Xiaofang Zhou and Dr. Li. So pathfinding or short-space computation is the fundamental operation for many real-life network applications. For example, when we do a loop planning in road network, we need to compute the fastest path, or when we compute the k-nearest neighbor or centrality between it, we also need to compute the shortest path. So in the social network, we need to compute the shortest path to analyze the collection or relationship between two nodes. And also in e-commerce transaction network, we can monitor the fraudulence based on the circle detection by computing the shortest path. So given a network represented as big G, we can denote the vertex set as big V and edge set as big E, and there is a weight associated with each edge. The path is a sequence of conjective edges, and the path length is the sum of these edge weights. The shortest path is the path of the minimal weight. And this query has been studied extensively in the past decades, but most of the case is in a static scenario. However, in a real life application, the network is changing all the time. So the dynamic shortest path query is of great importance, and we categorize them into 4 types, and they have different characteristic in terms of construction time, storage overhead, query time, and update time. In this work, we'd like to evaluate this algorithm systematically. The first reason is that, as mentioned before, DSP is of great importance. And secondly, we can't find one method optimal for all the circumstances. And thirdly, most of the existing papers are algorithm-oriented rather than program-oriented. And before the evaluation, let's look at this algorithm briefly. So for the Dijkstra search, for example, for the directed search, for example, the Dijkstra and AC algorithm, they find a path by searching a graph from scratch. And for the dynamic contraction hierarchy, there are 2 on the line index. The first one is contraction with pruning. So for example, the vertex W is contracted. We will only insert the shortcut from U to V, then the sum of edge weight from U to W and W to V is smaller than the shortest distance from U to V. Well, for the contraction without pruning, we will always insert shortcut from U to V, and both of them adopt the upward bidirectional way to process the query. Well, for the CHP, it uses the vertex-based index update method, while for the CHW, it uses the shortcut-based update. And for the dynamic hub labeling, the 2 on the line index, the first one is the pruned landmark labeling. It constructs the index based on the pruned Dijkstra search. Well, for the edge to edge, it builds the index based on the tree decomposition. And both of them make use of the 2-hop cover constraint to answer the query. So for the DPLS, it's update index by maintaining the Dijkstra search. And for both of the DPLP and DHTH, the update index based on propagation. Even though all these algorithms are totally different, but we find that they have one thing in common. It is the curse of increase update. So it means that a decrease update is relatively easier since the effective labor or shortcuts can be directly derived from the decreased age. Well, for the increase updates, extra information is needed. For example, for the DCH, we always need to store the weighted list path and supportive vertices. And for the deep dynamic PLL, we need to store the pruning point. However, this phenomenon is ignored in previous work. The first reason is that for those evaluation in the large tree-wise graph, most of them are only tested on the weighted graph. so we can get a very fast update with the parallel bitwise BFS. But when this method is extended to the weighted graph, especially for those graphs with large diameter, the data search is very slow. And for those evaluation in small tree-wise graph, they often use the DCHW. But this method has lots of redundancy with limited application. And then we set up the experiment. Firstly, we decide the 3 DSP problem dimension in terms of the update volume and frequency, query amount and frequency, and graph topology. We divide the whole time slot into multiple small time slots, and in each small time slot, we use the first part of time to update the index, and then reminding them to process the query. And then we design a dynamic network by set different update and query amount and frequency in both the synthetic and real-life networks, and compile this method based on different metrics. So when we let's look at the evaluation on a synthetic network in terms of the index construction time denoted by the bar and index size denoted by the ball. So DCHW has very dense shell card, and it can access the memory very easily. And for DCHP decrease case, it always has the smallest index size because of the probing power. And well, for the DCHP increase, its index size is larger because it needs to store a huge amount of weighted path. And then we evaluate this method in terms of the query time and update time. So you can see that the DS is the only algorithm that can work on every networks because it is independent of the index. For a dynamic HTH, even though it is very fast in query time, but it is limited in most graphs. And for the dynamic PLL, it is and for the DPLS, it is slowest for updates. And then we evaluate different algorithms in the same graph by comparing their throughput. So the x-axis is the length of the time slot, and the y-axis is the update lambda. So we can see that when the color of the gray is darker, it means that the update is more frequent. Then we can find that for different graphs they have their own suitable method. For example, for a lattice graph, the DS and DHTH is the most suitable method. And we also evaluate the same algorithm on different graphs, and can also decide the most suitable scenario or networks for different methods. For example, for the DCHW or DHTH, they are most suitable for the lattice graph. And then from this experimental result, we can get 3 guidelines. Firstly, we have 2 DSP factors. One is from internal, one is from external. And secondly, when we implement the DSP algorithm in real life, we can pick the algorithm by evaluate their query and update performance, and then compile their throughput in different scenarios. And lastly, there's some general DSP using scenarios. For example, for those situations with high update or query volume, then direct search is the best choice. At the same time, there's open challenges here. So the first one is that for the high dynamic scenario, we can always get very low throughput. And the second one is the curse of increase update. Even though we can hardly solve this problem theoretically, but it is necessary to find some practical solution urgently. And thirdly, how to combine this DSP algorithm in different scenarios is challenging. And lastly, we invalidate this algorithm in real life network, and the result corresponds to those in the synthetic graph.